Hello there, and a warm, gentle welcome to the Serene Scroll. I am so glad you could join me here in this quiet space. Perhaps the day has been full, the mind busy, the body tired. Here you can set all of that aside. You can allow your breath to soften your shoulders to release, and your thoughts to drift like clouds across a vast, peaceful sky. We are about to unfurl a story written in the stars, a journey into the deep and silent theater of the cosmos. And just before we begin, if these quiet explorations help your mind to settle or offer a peaceful way to end your day, consider a gentle tap on the like button and subscribing to the channel. It is a quiet way of helping these stories find others who might need a moment of calm. Now find a comfortable position, let your eyes gently close, and let us begin our journey. Take a slow, deep breath. Feel the air as it enters cool and clean, filling your lungs, and then feel it leave warm and soft, carrying with it any tension you might be holding. With each breath, allow yourself to sink a little deeper into comfort, a little deeper into the stillness of this present moment. Imagine the room around you growing quiet, the sounds of the world outside fading into a distant, gentle hum. Here, in this sanctuary of rest, there is nothing for you to do, nothing for you to solve. There is only the simple, peaceful act of being. Imagine yourself standing in an open field on a clear, moonless night. The air is cool on your skin, and the only sound is the soft whisper of a breeze through blades of grass. Above you, stretching from one horizon to the other, is the vast, dark ocean of the night sky. It is not an emptiness, but a presence, a profound and patient stillness. It is a quiet so deep it feels like a soft blanket wrapping the world in a peaceful embrace. Look up into that darkness. At first, it is simply black, an infinite canvas. But as your eyes adjust, points of light begin to emerge, one by one, then in clusters, then in a shimmering, countless multitude. They are diamonds scattered on black velvet, each one a tiny, perfect pinprick of light in the immense, silent expanse. This is the image of cosmic peace. It is the vista that has greeted humanity for millennia, a source of wonder, of navigation, of myth. It feels eternal, unchanging. The stars seem fixed in their positions, a permanent and reliable map in the heavens. This stillness is reassuring. It speaks of stability of a grand and orderly design that operates on timescales far beyond our own fleeting lives. But this deep, comforting quiet is a beautiful illusion. It is the illusion of a photograph capturing a single moment in time. The night sky is not a static painting. It is a dynamic, living ocean, and we are seeing it from the deepest, quietest trench. The light from these stars, these distant beacons, has traveled for an incredible length of time to reach your eyes. Think of the sky not as a ceiling, but as a deep, dark body of water. Each star is a lighthouse on a distant shore. The light it sends out is its signal, its story traveling across the waves of space and time. A lighthouse just a mile away sends a beam that reaches you in a fraction of a second. But these lighthouses are trillions upon trillions of miles away. Their light, though traveling faster than anything else in the universe, takes years, centuries, even millennia to cross the unfathomable gulf that separates us. The light you are seeing tonight did not leave its star tonight. It is an echo from the past. It is ancient history arriving in the present moment. The light from Alpha Centauri, our nearest stellar neighbor, began its journey over 4 years ago. When you see its gentle twinkle, you are seeing the star as it was 4 years in the past. The light from the bright star Vega set out on its voyage 25 years ago. The child who is just now seeing that light for the first time is seeing a photon that left its star before they were even born. Let your gaze drift to the constellation of Orion, the Great Hunter. Notice the reddish star on his shoulder, the mighty Betelgeuse. The light from that star has traveled for over 600 years. It left its source around the time the great cathedrals of Europe were being built during the late Middle Ages. All of human history that has unfolded since the Renaissance, the age of exploration, the Industrial Revolution, the entire modern world, all of it happened while that light was silently soaring through the void on its way to your eye tonight. You are in a very real sense looking back in time. The night sky is not just a space, it is a time machine. Each star is a window into a different epoch. We are seeing a collage of different pasts, all stitched together into the seamless illusion of a single present moment. This simple, profound fact changes everything. It means that the quiet, peaceful sky is a repository of stories. Each photon is a messenger carrying with it the tale of its origin. It tells of the thermonuclear furnace that forged it, the surface of the star it burst from, and the long, lonely journey it endured through the vacuum of space. Most of these stories are tales of quiet endurance, of steady burning light, of a life lived in slow, majestic balance. But this also means that what we see is not necessarily what is. A star whose light takes 1,000 years to reach us could have changed dramatically in that time. For all we know, in the 1,000 years that its light has been traveling, the star itself could have already vanished. We would not know. We would continue to see its light shining peacefully in our sky for the remainder of that 1,000-year journey. We would be watching a ghost, a beautiful, luminous memory of something that no longer exists. This is where the true nature of the cosmos begins to reveal itself. The stars are not eternal. They are not fixed, unchanging diamonds. They are physical entities. They are born, they live, and they die. They have lifespans, just as we do, but on a scale that is almost impossible to comprehend. Their lives play out over millions or even billions of years. A human lifetime is but a blink of an eye to a star. And yet, their life is a constant dramatic struggle. Every star you see is a battlefield. It is a place of unimaginable forces held in a delicate temporary truce. Deep within its core, the crushing force of gravity is trying to collapse the star into an infinitesimally small point. Pushing back against this immense pressure is the outward blast of nuclear fusion, the same process that powers a hydrogen bomb happening on a scale of millions of miles every single second. For as long as a star has fuel to burn in its core, these two forces remain in balance. Gravity pulls in, fusion pushes out. This equilibrium is what allows a star to shine steadily for billions of years, bathing its planetary systems in light and warmth. It is a gentle fire, a controlled explosion that lasts for eons. The vast majority of the stars we see are in this long, stable, middle-aged phase of their lives. They are the calm and steady lighthouses, their beams unwavering as they cut across the cosmic ocean. They are the suns of other worlds performing the same quiet, life-giving work as our own. Their light speaks of stability, of predictability, of a peace that lasts for ages. The tranquil appearance of the night sky is a testament to the longevity of this stellar balance. We are looking at a population of beings who are mostly in the prime of their very, very long lives. But this balance cannot last forever. The fuel for fusion is finite. For every star, no matter how large or small, there will come a time when the fuel in its core begins to run out. The gentle fire begins to sputter. The outward push of energy weakens, and the relentless inward pull of gravity begins to win the long war. What happens next depends entirely on the star itself. Its final act is pre-written in its birth, dictated by its mass. For some, the end is a quiet and graceful fading. But for others, the most massive and brilliant of stars, the end is anything but quiet. When their balance is broken, it shatters in the most spectacular and violent event the universe can produce. The stillness of the vast ocean is broken by a cataclysm of unimaginable power. A cosmic explosion that can outshine an entire galaxy of 100 billion stars. These events, the supernovae, are the universe's great forges. They are the moments when the quiet potential of the night sky is realized in a flash of brilliant, creative destruction. They seem like exceptions, like violent interruptions to the celestial peace. But they are not. They are a fundamental and necessary part of the cosmic story. They are the dramatic final chapters in the lives of the greatest stars. Before we can truly understand the sound and fury of these magnificent stellar deaths, we must first appreciate the quiet life that precedes them. We must understand the delicate dance of forces that defines a star for billions of years. To grasp the significance of the explosion, we must first know the stillness that it shatters. And so, let us turn our gaze from the entire ocean of night to just one of its lighthouses. Let us choose one of the steady, unassuming flames, a star much like our own sun. Let us explore the gentle fires that power an ordinary star, the source of its steady light, and the quiet, elegant physics that governs its long and peaceful middle age. To truly understand the grand, breathtaking explosions that light up the cosmos, we must first learn to appreciate the silence. We must begin not with a bang, but with a quiet and steady hum. The gentle, life-giving fire of an ordinary star, much like our very own sun. For in its long and predictable life, we find the baseline against which all cosmic drama is measured. Imagine, if you will, a vast, dark, and silent expanse of space. It is not empty. It is a cosmic nursery, a place called a nebula. It is a cloud of unimaginable size woven from thin wisps of hydrogen gas and fine grains of cosmic dust, the leftover ashes of stars that lived and died long ago. Within this cold, dark cradle the story begins. It is a story of gravity, the most patient force in the universe. For millions of years, gravity works its slow, persistent magic. It gently nudges particles of gas and dust together. A few molecules gather, then a few more. Their collective pull, however tiny, attracts others. A cosmic whisper becomes a gathering becomes a cloudlet, and a cloudlet begins to collapse under its own weight. Think of it as the quietest, slowest gathering of a storm in a sky that stretches for light years. As this cloud of primordial material pulls inward, it begins to spin slowly at first, then faster and faster, like a skater pulling in their arms. At its heart, a dense, warm core begins to form. This is a protostar, a star in its infancy, not yet shining with its own light, but glowing with the heat of its own compression. It is a seed of light waiting for the precise moment to awaken. For thousands of years, this core continues to gather mass, pulling in more and more material from the surrounding nebula. The pressure at its center builds, becoming immense, inconceivable. The temperature climbs from thousands to millions of degrees. And then something extraordinary happens. The pressure and heat become so intense that the very atoms of hydrogen at its core can no longer remain separate. They are forced together in an eternal embrace, fusing to become a new element, helium. This is nuclear fusion. It is not a fire in any sense that we would know on Earth. It is not a chemical burning. It is the fundamental alchemy of the universe, a process that unlocks a colossal amount of energy from the very fabric of matter. With this first spark of fusion, the protostar is truly born. It ceases to be a passive glowing ball of gas and becomes a star. It ignites, sending its first rays of light and warmth out into the darkness that has cradled it for so long. It takes its first radiant breath, and with that first breath begins a long and stable life, a life defined by a perfect, delicate balance. This balance, which physicists call hydrostatic equilibrium, is the secret to a star's peace. It is a silent cosmic dance between two immense and opposing forces. On one side, there is the relentless, crushing force of gravity. The star's own immense mass is constantly trying to pull everything inward to collapse the star into an infinitesimally small point. It is a constant inward pressure, a heavy weight that never ever rests. On the other side, there is the radiant energy pushing outward from the core. Every single act of nuclear fusion releases a torrent of photons, particles of light and heat that journey from the star's heart to its surface. This journey can take 100,000 years as each photon bounces from atom to atom, slowly making its way out. This outward flow of energy creates a tremendous pressure, a constant radiant sigh that pushes against gravity's grip, inward collapse, and outward radiation. For billions of years in a star like our Sun, these two forces are locked in a perfect stalemate. The star is not falling in on itself, nor is it flying apart. It is held in a state of exquisite tension, breathing in with gravity and breathing out with light. This is its main sequence, a long, quiet adulthood, where it steadily fuses hydrogen into helium, shining with a dependable and constant light. It is in this peaceful, balanced state that life can find a foothold on orbiting planets, basking in the reliable warmth of a star that has found its equilibrium. But nothing, not even a star, can maintain this balance forever. The fuel at its core is finite. After 10 billion years or so, an ordinary star like our Sun will have converted most of the hydrogen in its core into helium. The engine begins to sputter. With less fusion to power, the outward push gravity begins to win the long-held battle. The core, now made of helium ash, starts to contract under its own immense weight. This contraction paradoxically causes the star's outer layers to do the opposite. As the core shrinks and heats up, it ignites the remaining hydrogen in a shell surrounding it. This new furious burning produces a surge of energy far greater than before. The outward pressure overwhelms gravity in the star's outer layers, causing them to swell to an enormous size. The star begins to expand, growing 100, then 200 times its original diameter, swallowing any inner planets that might lie in its path. As its surface expands, its energy is spread over a much larger area, and so its surface cools, glowing not with a brilliant yellow-white, but with a deep, dusky red. The star has become a red giant. It is a final, magnificent bloom before the end, a vast, luminous ember in the twilight of its life. It is beautiful, but it is also a sign that the long, peaceful age is over. For a few 100 million years, the star lives this new, unstable life. Eventually, the core becomes hot enough to begin fusing its helium ash into heavier elements like carbon and oxygen, granting it a temporary reprieve. But this too is a short-lived phase. The star is too small, its gravity too weak to ignite these heavier elements. The fuel runs out for good. What happens next is not a violent explosion, but a gentle, graceful letting go. The star's final fusion pulses become unstable, creating a strong stellar wind that pushes its outer layers away. It is not a detonation, it is a serene exhalation. Over thousands of years, the star sheds its vast gaseous envelope into space. These expanding shells of gas, illuminated by the hot, tiny core left behind, create one of the most beautiful objects in the night sky, a planetary nebula. The name is an old misnomer, a relic from a time when astronomers with small telescopes thought these glowing rings resembled the faint disks of planets. They have nothing to do with planets. They are instead the ghost of a dying star. They are cosmic smoke rings, intricate webs of glowing gas, celestial dandelion seeds caught on the solar wind. They enrich the space around them with the carbon, oxygen, and other elements forged within the star's hard elements that will one day be gathered up by gravity to form new stars, new planets, and perhaps new life. It is the star's final act of creation, giving back its substance to the cosmos from which it came. And at the center of this expanding ethereal shroud, all that remains of the once mighty star is its core, a small, Earth-sized object of incredible density and heat. This is a white dwarf. It is the star's final quiet remnant. No fusion takes place within it anymore. It is a stellar corpse composed of a strange, compressed state of matter. A single teaspoon of it would weigh several tons. It no longer generates new heat. It simply radiates its leftover thermal energy into space like a hot coal taken from a fire. For trillions of years, a timescale far longer than the current age of the universe, this cosmic diamond will continue to cool. It will fade slowly from brilliant white to yellow to orange until finally it will become a cold, dark ball of crystallized carbon, a black dwarf drifting silently and invisibly through the endless night. This is the ultimate fate of more than 97% of the stars in our galaxy. A long, stable life, a beautiful and gentle end, and a quiet, eternal rest. It is a story of balance, of patience, and of a peace that lasts for eons. It is the story of the ordinary. But not all stars are born ordinary. Some are born of cosmic royalty, endowed from their first moments with dozens of times the mass of our sun. For these stellar giants, the story is not one of quiet balance, but of a life lived furiously and fast. Their hearts beat with a fiercer rhythm, their fires burn with an impossible heat, and their destinies are not written as a gentle exhalation into the dark. Their end is not a whisper, but a shout, a cataclysmic explosion that can outshine an entire galaxy. To understand them, we must now turn our gaze away from the gentle fires and look into the heart of a giant. But not all stars are born to live such long, placid lives. While stars, like our sun, represent the steady, reliable heart of a solar system, the cosmos is also home to true giants. These are the celestial leviathans, the titans that blaze with a ferocious, incandescent light and live lives that are breathtakingly short and impossibly dramatic. To find the origin of the universe's most powerful explosions, we must turn our gaze away from the gentle yellow dwarfs and toward these magnificent doomed stars. These are the O-type and B-type stars, cosmic royalty, draped in robes of brilliant blue-white light. They are born from the very same nebulae as their smaller siblings, but from the beginning, they are different. They are born of excess. Where a sun-like star sips its fuel, these giants gorge themselves. They can be dozens of times more massive than our sun, and hundreds of thousands, even millions of times more luminous. To stand on a planet in their orbit would be to know a sky dominated by a blinding blue-white furnace, a sun that would scorch and sterilize in equal measure. Their immense mass is both their glory and their curse. For in the heart of a star, mass dictates destiny. The more massive a star is, the more powerful its gravitational pull, the crushing inward force that tries to collapse it into a single point. To fight back against this relentless pressure, the star must burn its fuel at an astonishing rate. Its core must be hotter, its fusion reactions far more violent. And so while our sun will live for 10 billion years, these giants are lucky to see 10 million. They are the universe's most beautiful and tragic prodigal sons, burning through their vast inheritance of hydrogen in a cosmic blink of an eye. Their entire existence from birth in a dusty nebula to their final cataclysmic death can be shorter than a single geological epoch here on Earth. Their story is not a long, gentle hum. It is a rising, powerful crescendo building toward a final shattering chord. And to hear that music, we must journey deep inside into the very heart of the giant. At the beginning of its life, the massive star's core is a familiar place, operating on the same principles as our sun, but scaled to an almost unimaginable degree. Here, in a crucible of 15 million degrees or more, gravity has squeezed atoms of hydrogen so tightly that they overcome their natural repulsion and fuse together, creating helium. This is the first and longest act of the star's life. For millions of years, it is a hydrogen-burning furnace, a stable, if overwhelmingly powerful, engine. The outward pressure generated by this fusion perfectly balances the inward crush of gravity, holding the star in a delicate, momentary equilibrium. But even here, the seeds of its destruction are sown. The helium produced by the fusion, being heavier than hydrogen, sinks toward the very center of the core. Slowly, over millennia, a dense sphere of helium ash begins to accumulate. For a smaller star like our sun, this is a process that unfolds over billions of years. But in the giant, the furnace burns so hot and so fast that the core is choked with helium in a fraction of that time. When the hydrogen fuel in the immediate core is exhausted, the fusion engine sputters. For a moment, the balance is broken. Gravity begins to win. The core, now made almost entirely of helium, begins to contract under its own colossal weight. As it contracts, it heats up just as air becomes hot when compressed in a pump. The temperature soars, rising past 50, then 80, then 100 million degrees. At this mind-boggling temperature, a new fire is lit. The helium atoms themselves, the ash of the first fire, now become the fuel for the second. 3 helium nuclei begin to slam together with such force that they fuse, forging a new element, carbon. The star is reborn. A new wave of energy floods out from the core, pushing back against gravity, once more re-establishing a temporary truce. The star swells its outer layers, expanding and cooling, sometimes turning it into a red supergiant, a bloated luminous ember in the sky. On the inside, however, a new architecture is taking shape. The star is no longer a simple furnace. It is becoming a complex, layered factory. At its very center is a searing hot, carbon-producing core of burning helium. Wrapped around this is a shell where the remaining hydrogen is still hot enough to fuse into helium. It has developed concentric shells of fire, each layer defined by the fuel it consumes and the ash it produces. But this new stability is a fragile illusion, for the clock is ticking much faster now. While the star spent millions of years burning hydrogen, it will burn through its helium in a few 100,000. The process of creation has accelerated. Once again, the fuel in the core runs low. Once again, the heavier ash, this time carbon, sinks to the center and the core contracts. Gravity tightens its grip and the temperature and pressure skyrocket yet again. And here, the true alchemy begins. At a staggering 600 million degrees, the carbon atoms themselves are forced to fuse. In a series of complex reactions, they create heavier elements, neon, a little sodium magnesium. A new fire is lit, a carbon-burning furnace at the star's heart. The structure becomes even more intricate. We would now see a core of burning carbon surrounded by a shell of burning helium, which is itself surrounded by a shell of burning hydrogen. It has become a nested doll of creation, each layer hotter and denser than the one above it. This process, from one fuel to the next, now happens with bewildering speed. Each new stage of fusion provides less energy than the last, and therefore lasts for a shorter and shorter time. The star is in a desperate race against its own gravity, frantically trying to find a new source of fuel to keep itself from collapsing. It took millions of years to exhaust its hydrogen. It took hundreds of thousands of years to burn through its helium. It will burn all the carbon in its core in just a few centuries. When the carbon is gone, the core, now rich in neon contracts, and heats to over 1 billion degrees. The neon nuclei fuse, creating oxygen and magnesium. This stage lasts for less than a year. The oxygen then becomes the fuel. At 1.5 billion degrees, the oxygen atoms fuse to create silicon. This fire rages for only a few months, and then, in the final frantic days of the star's life, the silicon itself begins to burn. At a temperature of nearly 3 billion degrees, in a place so dense that a single teaspoon of its matter would outweigh a mountain, the silicon nuclei are violently rearranged, creating a host of heavier elements. But all roads lead to one final destination. The ultimate product of this last desperate act of fusion is iron. Here, at the very heart of the giant, a sphere of pure iron begins to grow. It is the star's final masterpiece and its death sentence. For millions of years, the star has survived by performing a magic trick. It fused lighter elements into heavier ones, and in doing so, released a tremendous amount of energy. It turned mass into light and heat, the very forces that held gravity at bay. But iron is different. Iron is the end of the alchemical road. It is the most stable atomic nucleus in the universe. To fuse iron into something heavier does not release energy. It consumes it. To split it apart also consumes energy. Iron is cosmic ash. It cannot burn. And so, as the final fires of silicon burning rage in a shell around it, the core of the star becomes a dead heart of iron. It is an impossibly strange place. It is no bigger than the Earth, yet it contains more mass than our entire sun, crushed into a sphere of unimaginable density. The pressure is so great that electrons have been squeezed from their atomic orbits, forming a bizarre sea of free-roaming particles. For all its density and heat, this iron core produces no new energy. It offers no resistance. It is just there. a gravitational sinkhole at the center of a dying god. All around it, the star's life continues in a frantic, layered symphony. In the shell just outside the core, silicon is fusing into iron, adding more and more dead ash to the central sphere. Further out, oxygen is burning into silicon, then neon into oxygen-carbon, into neon helium into carbon, and in the star's vast outer envelope, hydrogen is still fusing into helium. The star has become a perfect spherical onion, with each layer representing a different chapter of its life, all happening at once. But this is a story that is reaching its final page. The iron core grows mass piling onto it from the silicon-burning shell above. It reaches a critical point, a threshold discovered by the physicist Subramanian Chandrasekhar. It reaches a mass of about 1.4 times that of our Sun. At this point, the strange quantum pressure of the electrons, the very force that has been holding the core up against its own weight, can no longer resist the crushing force of gravity from all the star's outer layers. The furnace has gone out. The energy that supported a star for millions of years has been extinguished at its source. For one brief final moment, a profound and impossible quiet falls over the heart of the giant. The two great forces of the cosmos, the outward push of nuclear fire and the inward pull of gravity, are no longer in balance. The fire is gone. And gravity, the patient, relentless force that has been waiting since the star was born, finally has nothing standing in its way. The stage is set for the greatest act of collapse the universe has ever known. What happens next will not be measured in years or days or even seconds. It will be decided in the final millisecond. But not all stars are born to live such long, placid lives. While stars, like our Sun, represent the steady, reliable heart of a solar system, the cosmos is also home to true giants. These are the celestial leviathans, the titans that blaze with a ferocious, incandescent light, and live lives that are breathtakingly short and impossibly dramatic. To find the origin of the universe's most powerful explosions, we must turn our gaze away from the gentle yellow dwarfs and toward these magnificent doomed suns, and travel with them to the final moments of their reign. For millions of years, the great star has been a furnace of creation. In its heart, a colossal engine of fusion has tirelessly worked against the relentless crush of its own gravity. It began, as all stars do, by fusing the simplest element, hydrogen, into helium. When the hydrogen ran low, the core contracted and grew hotter, igniting the helium to forge carbon and oxygen. The cycle continued, a frantic and accelerating alchemy. Carbon became neon, became oxygen became silicon. Each stage was shorter, more desperate than the last. The hydrogen burning phase lasted millions of years. The silicon burning phase in the very end lasts for less than a day. The star has built up layers like an onion, with the heaviest elements sinking to the center. At its very heart, now, lies the final product of this furious chain of creation, a dense, searingly hot core of iron. And here, physics presents an insurmountable wall. For every element leading up to it, the act of fusion released a torrent of energy. This outward pressure, born of light and heat, was the star's only defense against its own immense mass. But iron is different. Iron is the ash of nuclear burning. To fuse iron into something heavier does not release energy. It consumes it. It is a one-way gate. The furnace, which for eons had roared with creative fire, has run out of fuel. For the first time in its life, the heart of the star falls silent. In this sudden, profound, quiet gravity, the patient and ever-present architect of the cosmos becomes the sole victor. There is nothing left to push back. The equilibrium that defined the star's entire existence is shattered. The event that follows is not an explosion, not yet. It is the opposite. It is an implosion of unimaginable speed and violence, a silent internal catastrophe that unfolds in less time than it takes to draw a breath. Let us slow time itself and witness the final millisecond. The iron core is a sphere roughly the size of planet Earth, but it contains the mass of 1.5 suns. The moment fusion ceases, this sphere begins to collapse under its own weight. The outer layers of the star, the vast gaseous envelopes of hydrogen, helium, and silicon, are for now completely unaware of the verdict that has been passed in the core. They continue to float in the serene vacuum of space, shining as they always have. The message of the core's death traveling outward at the speed of sound through the stellar plasma will not reach them in time. What is about to happen happens to the core alone. The collapse begins. At a staggering 25% of the speed of light, the material of the core plummets inward toward the center. The density and temperature skyrocket to levels that defy easy comprehension. In this crucible, the atoms themselves are dismantled. The crushing force is so great that the very structure of matter begins to fail. The first line of defense is a quantum mechanical principle known as electron degeneracy pressure. This is a fundamental rule of the universe that states no two electrons can occupy the same quantum state in the same place. It is an expression of the sheer territoriality of matter at its most fundamental level. For a moment, this ghostly, powerful pressure fights back against gravity. It is the only thing preventing the core from collapsing into a singularity. It is like an invisible, infinitely rigid wall, but the mass of the collapsing core is too great. Gravity is relentless. It presses harder and harder still. The inconceivable pressure finally overwhelms the resistance of the electrons. The wall breaks, and here matter is forced to do something extraordinary. The gravitational pressure becomes so immense that it physically squeezes the electrons into the atomic nuclei. Protons, the positively charged particles in the core of each iron atom, are forced to merge with the negatively charged electrons. When a proton and an electron combine, they neutralize each other, forming a neutron and releasing a tiny ethereal particle called a neutrino. This process, called electron capture, happens all at once throughout the entire core. It is a moment of profound transformation. The core is no longer made of iron. It is being transmuted into a sphere of pure, densely packed neutrons. This is the birth of a proto-neutron star. The change is catastrophic for the core's structure. Electrons provided much of the pressure holding the core up. By vanishing into neutrons, they remove that support. The collapse, which had been momentarily slowed, now accelerates into a final headlong freefall. But it is the other product of this reaction, the neutrino, that holds the key to what comes next. For every proton and electron that merge, a neutrino is born. In a fraction of a second, an unbelievable number of them, 10 to the power of 58 flood out of the collapsing core. These are ghostly particles. They interact so weakly with other matter that they can pass through an entire planet of lead without stopping. And so, while the light from this event is still trapped deep within the star's opaque outer layers, the neutrinos stream out unimpeded, carrying away a colossal amount of energy. They are the first messengers, the silent, invisible announcement to the universe that a giant has fallen. They are the star's departing soul, fleeing the wreckage at nearly the speed of light. Back in the core, the freefall continues. The sphere that was once the size of the Earth has now shrunk to the size of a large city, perhaps just 20 kilometers across. The density is beyond anything found in the universe, save for a black hole. A single teaspoon of this material would weigh more than all of humanity combined. It seems nothing can stop the collapse now. But physics has one final defense. Just as electrons resist being crushed together, so do neutrons. This is neutron degeneracy pressure, and it is orders of magnitude more powerful than the electron pressure that has already failed. When the collapsing core reaches this ultimate point of compression, it slams headfirst into this unyielding quantum barrier. The collapse, which had been accelerating to fantastic speeds, comes to a dead stop in an instant. The material that was plummeting inwards at a quarter the speed of light has nowhere to go. It doesn't just stop, it rebounds. The core, having been compressed far beyond its natural equilibrium, now violently bounces back. It is not an explosion in the conventional sense, not a fire, not a chemical reaction. It is a purely mechanical event of cosmic proportions. Imagine dropping a perfectly elastic steel ball onto a perfectly solid steel anvil. The ball doesn't just stop, it bounces back with nearly all of its original energy. Now imagine that ball weighs more than the sun. This rebound creates a shockwave of unimaginable power. A spherical wall of pure kinetic energy and pressure erupts from the surface of the newly formed neutron core. This is the moment of conception for the supernova. The entire process, the shutdown of fusion, the gravitational collapse, the creation of the neutron star, and the final thunderous bounce, has taken less than 1 second. The silent inward breath is complete. Now the star is poised for a universe-shaking exhale. But the journey is not over. This nascent shockwave, the herald of the coming fire, is born deep inside the star. It now faces a Herculean task. It must fight its way out. Ahead of it lie the still collapsing outer layers of the star, thousands of kilometers of dense iron, silicon, and oxygen that are still raining down, oblivious to the bounce that has already happened. The shockwave must push against this incredible torrent of infalling material, a celestial tide that threatens to crush it before it can ever reach the surface. For a few crucial milliseconds, the fate of the star hangs in the balance. Will the shockwave have enough energy to blast through and trigger the glorious explosion we call a supernova? Or will it stall, its energy sapped by the sheer weight of the star above, causing the entire mass to collapse directly into a black hole with barely a whimper? The heart of the star, once a sphere the size of a planet, is now a city-sized kernel of impossible density. It has inhaled the cosmos, and now held for a fraction of a millisecond in a state of perfect violent equilibrium, it is ready to exhale. The shockwave, a ghost of the core's own rebound, begins its journey outward, carrying with it a message of annihilation and creation that is about to tear through the veil of the star and announce itself to the universe. But not all stars are born to live such long, placid lives. While stars, like our sun, represent the steady, reliable heart of a solar system, the cosmos is also home to true giants. These are the celestial leviathans, the titans that blaze with a ferocious incandescent light, and live lives that are breathtakingly short and impossibly dramatic. To find the origin of the universe's most powerful explosions, we must turn our gaze away from the gentle yellow dwarfs and toward these magnificent, doomed giants. For within them, a final catastrophic moment is brewing. For a fraction of a second, an entire universe of physics holds its breath. The iron core, now no larger than our own small Earth, but containing more mass than our Sun, has lost its fight against gravity. The outward push of fusion has ceased forever. In less than a quarter of a second, a span of time too brief for the human mind to truly register, the core collapses. It is an implosion of unimaginable speed and violence. The outer edge of the core plummets inward at nearly a quarter of the speed of light, crushing itself into a state of matter so dense that a single thimbleful would outweigh all of humanity combined. Protons and electrons are squeezed together with such impossible force that they merge, transforming into a sea of neutrons and releasing a whisper of ghostly particles. The core has become a proto-neutron star, a solid ball of pure nuclear matter. And here, in this moment of ultimate compression, something extraordinary happens. The collapse stops. It doesn't slow down. It stops. The core, having been crushed beyond the limits of known physics, rebounds. It bounces back like a cosmic spring, unleashing a shockwave of monumental power. This is the trigger. This is the spark that lights the fuse of the greatest firework in the universe. But the first announcement of this event is not a flash of light. It is something far stranger, far more elusive. Before any telescope can register a change, a phantom blast wave of neutrinos erupts from the core. These are the ghost particles of the cosmos, so ethereal they can pass through light years of solid lead without interacting with a single atom. As the core was crushed, a cataclysmic number of them were born, more neutrinos than there are atoms in all the galaxies we can observe. They carry away almost all the energy of the collapse, a silent, invisible tsunami that floods the universe. As they pour outwards, they pass through the star's own collapsing outer layers, as if they weren't there, streaming into the void at the speed of light. If you were standing on a planet in a nearby star system, trillions of these phantoms would be passing through your body at this very moment, their silent journey. The only sign that a star somewhere out in the deep has just died. They are the heralds, the secret messengers carrying the news of a king's fall long before the kingdom sees the smoke. Back within the dying star, the true physical battle has begun. The shockwave born from the core's rebound now begins its ferocious journey outward. It is a wave of pure pressure and energy, a wall of force plowing back up through the very layers of matter that are still collapsing inward. This is no simple explosion. It is a struggle against the dying star's own immense gravity. For a moment, the shockwave stalls, its energy sapped by the sheer weight of the infalling star. It seems as though the explosion might fail, that the star might collapse directly into a black hole, its final light trapped forever. But the neutrinos, those ghost particles that fled, first play one final crucial role. While most of them escape cleanly, a tiny fraction less than 1% slam into the dense, superheated gas just behind the shockwave. It isn't much, but it's enough. That tiny deposit of energy reinvigorates the stalled shockwave, giving it the final desperate push it needs to overcome gravity and tear the star apart. Now its victory, assured, the wave of annihilation and creation accelerates. It rips through the stellar layers in reverse order of their creation. It blasts through the shell of silicon and sulfur, then the shell of oxygen and neon, then carbon, then helium, and finally the vast outer envelope of hydrogen. Each layer, which took millennia to form, is vaporized in mere hours. And in this fleeting, violent passage, something miraculous occurs. The temperatures and pressures behind the shockwave become so extreme that they trigger a final, frantic burst of nuclear fusion. This is not the slow, steady fusion of a star's life. This is explosive nucleosynthesis. In this cosmic crucible, for just a few moments, the conditions are right to forge elements far heavier than iron. The universe is seeded with its most precious materials. Atoms of silver, tin, and iodine are created. Gold, the substance of crowns and currency, is born in the heart of this detonation. Platinum, the catalyst for countless reactions on Earth, finds its origin here. The rare earths that power our modern electronics, the uranium that fuels our power plants and our fears, all are synthesized in the final agonizing moments of this star's death. The star in its demise is performing its last and most generous act. It is forging the very elements that will one day make rocky planets complex chemistry and perhaps even life itself. It is a funeral pyre that builds the cradle of a new world. Finally, after hours of struggle, the shockwave reaches the star's surface. The star's photosphere, its visible edge, begins to swell and brighten with an unholy light. Then it breaks through. The star erupts. A supernova is born. The light that is released is almost beyond comprehension. For a few weeks, this single dying star will outshine its entire home galaxy. It will blaze with the light of 100 billion suns, a temporary beacon, visible across millions, even billions of light years. It is a celestial flower of impossible scale, its petals, made of incandescent gas, blooming in a fraction of a second. If our own sun were to be replaced by a supernova, the initial flash would be so bright it would scorch the daytime side of the Earth, and its light would be brilliant enough to read by on the surface of Pluto. This ancestral light, the final testament of a giant star's life, now begins its own long journey. It is a wave of information, a postcard from the past, carrying the story of the star's life and the elemental recipe of its death. It will travel through the cold, empty void for thousands or millions or hundreds of millions of years. It may travel for so long that when it finally arrives at the lens of a future telescope, the civilization that built it may not have even existed when the star first died. The light tells a story of both an ending and a beginning, the end of a star, and the beginning of the journey for the atoms it created. As the weeks turn into months, the initial blinding flash begins to fade. But the spectacle is far from over. The material of the star, now superheated and enriched with newly forged heavy elements, continues to expand outwards in a vast glowing cloud. This cloud, a ghost of the star that once was, is a chaotic, beautiful tapestry of gas and dust glowing in vibrant colors as it collides with the interstellar medium around it. The explosion has ceased, but its legacy is just beginning to unfold, painting a masterpiece across the canvas of space. The celestial firework has gone off, and now we are left to gaze at the slowly expanding, intricate smoke. This beautiful expanding shroud of stardust holds the raw materials for future generations of stars and planets. But what of the heart of the explosion? What remains at the center of this ghostly gilded remnant, the place where the star's core made its final stand? And what new secrets will this expanding cloud reveal as it cools and thins, becoming a nursery for a new cosmic dawn. The blinding flash recedes, the roar of 1,000 suns fades into an impossible silence across the vacuum of space. Where a colossal burning star once held court, there is now a ghost. But this is not a ghost of sorrow or emptiness. It is a specter of breathtaking beauty, an expanding masterpiece of light and color painted across the canvas of the void. This is the gilded remnant, the final glorious exhalation of a star that lived fast and died brilliantly. For thousands of years, the light from the supernova travels a silent herald of the cataclysm that gave it birth. And when it finally reaches us, when our telescopes gaze upon the place where the star once was, we see not a wound in the fabric of space, but a celestial tapestry. We see nebulae like the Veil or the Crab, vast intricate clouds of gas and dust still blossoming outwards from the point of detonation. They are ethereal structures threaded with filaments of incandescent hydrogen, glowing emerald with ionized oxygen, and shimmering with the light of elements forged in the heart of the explosion. These are not chaotic clouds of debris. They are cosmic sculptures shaped by shockwaves and magnetic fields into delicate web-like patterns. The light we see is the glow of memory, the remnant heat and energy of the star's final moments, a lingering warmth that will slowly cool over hundreds of thousands of years. The Crab Nebula, a famous remnant in the constellation of Taurus, is a perfect portrait of this afterlife. To our eyes, it is a tangled luminous cloud, 6 light-years across, and still expanding at over 1,000 kilometers per second. We know its birthday with remarkable precision. In the year 1054, astronomers in China, Japan, and the Arab world recorded the appearance of a guest star in the daytime sky, a point of light so brilliant it was visible for weeks. They were witnessing the supernova in real time. What they saw was the flash. What we see now, nearly a millennium later, is the beautiful, ever-unfurling consequence. It is a direct link between human history and cosmic history, a reminder that the sky above is not a static backdrop, but a dynamic, evolving stage where the greatest dramas unfold. But the beauty of these remnants is more than just visual. It is foundational, for within these glowing clouds are the very seeds of future worlds. Before the first generation of massive stars lived and died, the universe was a far simpler place, composed almost entirely of hydrogen and helium, the lightest elements forged in the Big Bang. There was no carbon for life, no oxygen to breathe, no silicon for rocks, no iron for blood. These heavier elements, everything that makes up our planet and our bodies, had to be created. They were forged in the nuclear furnaces of stars, and most crucially, in the unimaginable pressures and temperatures of the supernova explosions themselves. The supernova, in its final act of self-destruction, becomes an act of cosmic creation. It is the ultimate alchemist, transmuting simple elements into gold, platinum, uranium, and scattering them like a farmer, sowing seeds across the interstellar medium. The expanding remnant is a cosmic garden, enriching the sterile hydrogen clouds of the galaxy with the complex ingredients needed for the next generation of stars and planets. The iron that gives our blood its strength, the calcium that forms our bones, the carbon that is the scaffolding of all known life. Every atom of these elements within you was billions of years ago ejected into space by a dying star. You are in the most literal sense made of stardust. This gilded remnant is not just a monument to a dead star. It is the womb of future possibilities, the promise that from even the most violent endings can come the most profound new beginnings. As we look deeper into this celestial garden, past the glowing filaments and shimmering veils of gas, our gaze is drawn to the center. The outer layers of the star were blown away, but what happened to its core? The heart of the star, which for millions of years withstood the crushing force of its own gravity, has now finally succumbed. Here in the quiet aftermath, we find some of the most exotic and mysterious objects in the entire universe. For a star up to about 20 times the mass of our Sun, the core collapses with such force that protons and electrons are squeezed together to form neutrons. The entire core, a sphere that was once millions of kilometers across, is crushed down into an object barely 20 kilometers in diameter, the size of a city. This is a neutron star. The name is simple, but the reality is almost beyond comprehension. It is an object so dense that a single teaspoon of its material would have a mass of billions of tons, equivalent to an entire mountain compressed into a sugar cube. Its gravitational pull is hundreds of billions of times stronger than Earth's. It is a single gigantic atomic nucleus, a sphere of pure, degenerate neutron matter. The formation of a neutron star is an act of extreme preservation. As the star's core collapsed, it conserved its angular momentum, just as an ice skater spins faster when they pull their arms in. A star that may have rotated once every few weeks is now a tiny sphere spinning hundreds of times every single second. This rapid rotation, combined with the star's incredibly powerful magnetic field, which is also compressed and amplified, turns the neutron star into a cosmic lighthouse. As it spins, it sweeps powerful beams of radiation, radio waves, X-rays, and even visible light out into space from its magnetic poles. If one of these beams happens to sweep across our line of sight here on Earth, our radio telescopes will detect a pulse, a brief flash of energy that repeats with astonishing regularity. This is a pulsar. When pulsars were first discovered in 1967 by Jocelyn Bell Burnell, their precise clockwork signals were so unnatural, so unlike anything seen before, that they were playfully labeled LGM-1 for little green men. It seemed more plausible for a brief time that they were artificial beacons from an alien civilization than a natural phenomenon. But we soon understood. The ticking clock was the frantic spin of a dead star's heart. At the center of the Crab Nebula, for instance, lies the Crab Pulsar, a neutron star spinning 30 times a second, its lighthouse beams energizing the entire nebula and making it glow. It is the engine hidden within the ghost, the tiny, powerful heart still beating within the magnificent corpse. It is a testament to the strange and beautiful physics that governs the cosmos, a celestial metronome counting out the seconds in the aftermath of creation. But what if the star is even more massive? What if after the supernova, the collapsing core is so heavy, more than about 3 times the mass of our Sun, that nothing can stop its collapse? Not the pressure of electrons, not even the immense resistance of neutron matter itself. In this case, gravity wins its final absolute victory. The core continues to collapse, shrinking past the point of a neutron star, crushing itself down, down until it becomes a point of infinite density and zero volume. It becomes a singularity. Around this point, the fabric of space-time itself is warped so severely that it creates a region from which nothing, not even light, can escape. This is a stellar mass black hole. Unlike the glowing remnant or the pulsing neutron star, a black hole is a monument of pure absence. It does not shine. It consumes. It does not radiate. It warps. It is defined not by what it is, but by the boundary around it, the event horizon. This is not a physical surface, but a threshold, a point of no return. Cross it, and you are irrevocably drawn towards the singularity at the center. The supernova remnant in this case might look similar from a distance, a beautiful expanding cloud of enriched gas and dust. But at its heart, there is no lighthouse, no ticking clock. There is only a quiet, perfect darkness, a gravitational abyss. For many years, these objects were purely theoretical mathematical ghosts in Einstein's equations. But we now see their influence everywhere. We see stars orbiting invisible partners, their paths dictated by the immense gravity of a black hole. We see matter from companion stars being siphoned off, forming a superheated, glowing accretion disk as it spirals towards the event horizon, screaming in X-rays before it vanishes forever. The supernova in this final act does not just create the building blocks of life. It creates the most profound and fundamental mystery in all of physics, a tear in the fabric of reality itself. From a single violent death comes this incredible diversity of cosmic legacies, a beautiful life-giving nebula, a hyper-dense spinning pulsar, or a silent, enigmatic black hole. The supernova is not an end, but a transformation. It is the universe recycling itself on the grandest possible scale, ensuring that the death of one generation of stars provides both the material and the mystery for the next. The elements scattered from these gilded remnants would eventually coalesce and form new stars, new planets, and on at least one of those planets life that could look up at the night sky and wonder where it all came from. For a long time, we believed that the supernova was the most powerful explosion the universe had to offer. It was the undisputed king of cosmic fireworks, the loudest and brightest event on the celestial stage. And in the visible light that our eyes can see, it is. We measured their energy, cataloged their beautiful remnants, and felt we had a grasp on the limits of cosmic violence. But the universe is subtle. Its greatest secrets are not always broadcast in the light we are accustomed to. Hidden from our view, occurring in a flash of energy far more powerful than visible light, was another class of explosion altogether. For decades, a secret lay hidden in the sky, a whisper of a fire so immense it could dwarf a supernova, a fleeting burst of power that would rewrite our understanding of death in the cosmos. While the ghost of a dead star paints its slow, magnificent masterpiece across the void, a masterpiece that can be admired for millennia, the universe was whispering another more urgent secret. This was not a story told in gentle, expanding nebulae of gas and dust. It was a story told in a flash, a story written in a form of light entirely invisible to our eyes, a language of pure energy that arrived without warning and vanished without a trace, leaving behind only a profound and unsettling silence. For a time, we were completely unaware of these cosmic pronouncements. Our eyes, so attuned to the gentle shimmer of starlight, were blind to the most violent events the universe had to offer. The secret was kept, not because the cosmos wished to hide it, but because we had not yet built the right ears to listen. The story of how we began to hear this secret does not begin in a grand observatory with a telescope aimed at the heavens. It begins here on Earth during a time of deep suspicion and terrestrial anxiety. In the 1960s, humanity's gaze was turned inward. The Cold War cast a long shadow across the globe, and the superpowers watched each other with a guarded electronic stare. As part of this global watch, a series of satellites were launched into high orbit. They were called The Vela satellites, from the Spanish word for watchman. Their mission was not to study the stars, but to enforce a human treaty. They were designed to detect the telltale high-energy signature of a nuclear bomb detonated in space, listening for the very specific flash of gamma radiation that such a weapon would produce. These silent watchmen did their job perfectly. They listened, and soon enough, they detected flashes of gamma rays. On July 2, 1967, the first confirmed event was recorded. A brief, intense burst of energy, then another, and another. But as the scientists analyzed the data, a deep puzzle emerged. The signals were not coming from near Earth, nor from the Moon. They weren't coming from anywhere within our solar system. The direction of the flashes was random, arriving from all corners of the sky with no discernible pattern. They were isotropic, meaning they seemed to have no preference for the plane of our own Milky Way galaxy. Furthermore, the light profile of the bursts, the way their energy rose and fell, looked nothing like the signature of a man-made device. This was something else, something natural, something profoundly alien. For years, this discovery was a closely guarded secret locked away in classified files. A handful of scientists at the Los Alamos National Laboratory were grappling with a cosmic mystery born from a terrestrial conflict. What in the universe could produce such an astonishing amount of high-energy radiation for only a few fleeting seconds and then simply disappear? It was the ultimate astrophysical puzzle. Imagine standing in a completely dark, planet-sized room, and somewhere within it, a single camera flash goes off for 1 second. Your task is to find not only where the flash came from, but what caused it, with no other clues. This was the scale of the challenge. The universe was screaming, but the sound was so short and its source so fleeting that we could do nothing but register the shock. When the discovery was finally declassified and shared with the wider astronomical community in 1973, it ignited decades of debate. The central question was one of distance. Were these flashes coming from sources relatively close by, within our own Milky Way galaxy? If so, they would be powerful. Certainly, but perhaps not unimaginably so. They might be caused by some exotic phenomenon related to neutron stars or flare stars. Or, and this was the far more dramatic possibility, were they coming from the very edges of the observable universe, from galaxies billions of light years away? This was not just a question of geography. It was a question of energy. The brightness of a light follows an inverse square law. A light source twice as far away appears 4 times dimmer. If these bursts were truly cosmological, originating in the deep past of the universe, then to appear as bright as they did to our satellites, their intrinsic power had to be beyond all comprehension. A nearby firefly can seem as bright as a distant lighthouse. Without knowing the distance, astronomers couldn't tell if they were witnessing a cosmic firefly or a cosmic lighthouse. If they were lighthouses, then for a few brief moments, a single gamma-ray burst, or GRB, would have to outshine its entire host galaxy. For a few seconds, it would be the brightest object in the entire universe. For nearly 30 years, the mystery deepened. Telescopes would scan the patch of sky where a burst had been detected, only to find nothing. The source was a ghost. There was no fading ember, no supernova remnant, no strange star left behind to study. The event was simply too fast. By the time a gamma-ray satellite had registered a burst and relayed the information to ground-based telescopes, the show was over. The sky was quiet again. A whole branch of astronomy was dedicated to studying an event they could never actually see with a traditional telescope. They were chasing shadows, analyzing the ghostly gamma ray signature, and trying to build theories from those few photons alone. The breakthrough, when it came, was a masterpiece of international collaboration and engineering. An Italian-Dutch satellite named Beppo-Sax, launched in 1996, was designed with a specific goal in mind: to catch these ghosts. It carried not only gamma-ray detectors, but also X-ray telescopes. The idea was that the initial violent explosion might create a slightly longer-lasting afterglow in lower-energy X-rays. Beppo-Sax could detect the gamma-ray flash and, in a matter of minutes, reorient itself to focus its X-ray cameras on that precise location. This would give astronomers a much smaller patch of sky to search with their powerful ground-based telescopes. On February 28, 1997, the strategy paid off. Beppo-Sax detected a burst GRB 970228. It swiftly pinpointed the location with its X-ray instrument and broadcast the coordinates to observatories across the Earth. Telescopes on the ground swiveled to the target, and for the very first time they saw it. A tiny, faint pinpoint of light that had not been there the day before. Over the next few days, they watched as this pinpoint of light slowly, gracefully faded away. This was it, the afterglow, the smoking gun. Now astronomers could do what they do best. They could analyze that faint light. By passing it through a prism-like instrument called a spectrograph, they could see the telltale fingerprints of its journey across the cosmos. The light was stretched, its wavelength shifted toward the red end of the spectrum, a phenomenon known as redshift. This redshift is the universe's own yardstick. The greater the redshift, the farther away the object is, and the faster it is receding from us due to the expansion of the universe. The redshift of GRB 970228 was enormous. It told a story of a journey that had lasted over 8 billion years. The flash that the Vela satellites had first mistaken for a human weapon was in fact an echo from a time when the universe was barely half its current age. The distant lighthouse theory was correct. The energy calculations were redone now with a known distance, and the numbers were stupefying. They defied belief. The power unleashed by a gamma-ray burst in a matter of seconds was more than our own sun will produce in its entire 10 billion-year lifetime. It was a release of energy that dwarfed a supernova by a factor of hundreds. We had discovered a new supreme class of cosmic cataclysm. As more bursts were detected and their afterglows studied, a pattern began to emerge from the chaos. The bursts were not all the same. They seemed to fall into two distinct families. There were the short-duration bursts lasting less than 2 seconds. These were violent, sharp, and even more energetic in their brief lifespan. Their origin remains one of the deepest mysteries, though evidence points toward the collision of two incredibly dense objects like neutron stars or black holes. But there was another family, the long-duration bursts, lasting anywhere from 2 seconds to several minutes. And these bursts had a fascinating calling card. Their afterglows were almost always found residing in distant galaxies that were frantically busy, blazing with the light of new star formation. And in some cases, as the afterglow of the GRB faded, the distinct light of an underlying supernova would begin to swell like a second slower echo. The connection was undeniable. These long bursts were linked to the death of stars. But this presented a new profound puzzle. We had just come to understand the awesome power of a supernova, the final explosive collapse of a massive star. Yet a gamma ray burst was an entirely different order of magnitude. A supernova, for all its power, is an egalitarian explosion. It blasts its energy outwards in all directions, a mostly spherical shockwave of light and matter. Such an inefficient scattered blast could never generate the focused intensity needed to be seen from across the universe. So what kind of death was this? If a supernova is the final roar of a dying star, then a gamma ray burst is something else entirely. It is not a roar, but a shriek. A focused, directed, coherent beam of energy, a searing lance of light that punches clean through the fabric of the cosmos. This could not be the death of just any massive star. This had to be the death of a true titan, a star so colossal, so unstable, that its demise creates a phenomenon fundamentally different from all others. It is a death that does not just explode, but collapses with such ferocity that it rips a hole in space and time itself, and from that maelstrom unleashes the hypernova's cry. This profound and unsettling silence was the clue. It was a silence that spoke louder than any explosion. For decades, astronomers had been capturing these fleeting whispers from the cosmos, bursts of gamma radiation, the most energetic form of light, that would flare into existence and then vanish in minutes, sometimes seconds. They were named simply for what they were: gamma ray bursts. They were the brightest electromagnetic events known to occur in the universe, outshining entire galaxies for their brief duration. Yet when telescopes swiveled to look at the source in visible light, they often found nothing. No fading supernova, no lingering nebula, just the quiet, empty blackness of intergalactic space. It was as if the universe had screamed at the top of its lungs and then pretended nothing had happened. What could create such an immense phantom? What kind of stellar engine could pour out more energy in 10 seconds than our sun will in its entire 10 billion year lifetime, and do so without leaving a visible trace? The answer, when it began to form, was more terrifying and more magnificent than a simple explosion. It wasn't an explosion at all, not in the way we understood it. It was a directed verdict, a sentence carried out with the precision of a spear, not the chaos of a bomb. To understand this event, we must first imagine its architect. We must travel to a star so massive it stretches the very definition. Not just a supergiant, but a titan among titans. A star born with perhaps 40, 50, or even 100 times the mass of our sun. In its final days, it would look nothing like the familiar yellow dwarf of our own system. It would be a Wolf-Rayet star, a celestial behemoth that has already blown away its vast outer layers of hydrogen, exposing its furiously hot core of helium and heavier elements. Its surface is not a gentle sea of light, but a roiling tempest, its stellar winds howling into space at millions of miles per hour, stripping it of its own substance. But there is another critical ingredient to this cosmic recipe. This star is not just massive, it is spinning with a ferocious, dizzying speed. Perhaps it was born this way, or perhaps it siphoned material from a companion star in a gravitational waltz, stealing not just mass, but momentum, spinning itself faster and faster, like a dancer pulling in their arms. This rotation is the key. It is the spring being wound, the potential energy being stored for the final cataclysmic release. For this star, the end does not come as it does for its smaller cousins. When its core runs out of fuel gravity, the patient, relentless force of the cosmos finally wins its ultimate victory. The core itself, more massive than several suns, begins to collapse. But there is no iron core to halt the fall. There is no force in nature strong enough to push back. The material does not bounce. It does not create a shockwave that rips the star apart in a glorious symmetrical supernova. Instead, the core collapses completely, unstoppably. In less than a second, it plunges past the point of no return, crushing itself out of existence and giving birth to a black hole in the very heart of its own dying body. Imagine the scene: a brand new singularity, an infant abyss of space-time, now sits at the center of the still intact, colossal star. The star's outer layers, still blissfully unaware of the verdict passed in the core, now begin their final fatal descent. Trillions upon trillions of tons of superheated plasma rain down toward the new central black hole. But because the star was spinning so rapidly, this material cannot fall straight in. Its own angular momentum saves it from immediate oblivion, forcing it into a orbit. A temporary reprieve that builds the engine of destruction. A vast swirling vortex of matter forms around the black hole. This is the accretion disk, but it is no ordinary disk. It is a cauldron of unimaginable density and heat, a cosmic maelstrom where friction heats the plasma to billions of degrees. Magnetic fields dragged along with the spiraling matter are twisted and amplified into structures of immense power, wound tighter and tighter like cosmic rubber bands. This accretion disk, this spinning torment of a star feeding its own demise, becomes the most powerful engine in the known universe. This engine is now overflowing with energy. It must be released. But where can it go? It cannot escape sideways, for the path is blocked by the thick, dense, still falling layers of the star itself. There is only one escape route: up and down, along the poles of rotation, the path of least resistance. And so it happens. The coiled-up magnetic energy and the intense pressure within the disk find their release. Two opposing jets of matter and energy, narrow and perfectly focused, are launched from the poles of the black hole. These are not jets of fire or light in the conventional sense. They are tightly collimated beams of plasma accelerated to 99.99% the speed of light. They are cosmic drills, needles of pure energy punching their way out from the star's dying heart. For several seconds, these relativistic jets tunnel through the body of the star that created them. They are an explosion turned inward, a focused blast, carving a path through its own parent. When they finally breach the star's surface and erupt into space, they unleash the torrent of high-energy photons we detect as a gamma-ray burst. This is the piercing scream we hear across billions of light years, the lighthouse beam finally sweeping past our line of sight. This model, the collapsor model, explains the silence. The energy isn't spherical, it's beamed. The star does not detonate like a firework, casting its light in all directions for all to see. It dies like a lighthouse, casting its intense, powerful beam into two narrow cones. If you are in the path of that beam, you witness the most luminous event in the universe. If you are standing even slightly to the side, you see nothing at all. For every one gamma-ray burst we observe, it is thought that hundreds more occur, their cosmic searchlights sweeping harmlessly past our planet, their silent screams lost to us forever in the void. Only after the jet has fired, after the gamma rays have begun their long journey across the cosmos, does the rest of the star finally tear itself apart. The energy from the jets helps to blow the remaining layers into space in an explosion of such violence that it dwarfs a typical supernova. We call this a hypernova. It is this secondary, more conventional explosion that creates the faint, rapidly fading optical afterglow that astronomers race to find in the minutes and hours following a GRB detection, the final smoldering ember of a truly titanic death. For decades, this was the only story we knew for these cosmic apparitions, a long drawn-out cry lasting anywhere from 2 seconds to several minutes, heralding the death of a single, spinning giant star. This story fit the data beautifully, and it painted a picture of a universe capable of a focused, targeted violence that was humbling to comprehend. But the universe, it turned out, had another secret. Sometimes, the signal that reached our satellites was not a cry, but a chirp. A flash of gamma rays so brief, so impossibly fast, lasting less than 2 seconds, sometimes just a few milliseconds, that it simply could not come from the slow, messy collapse of a star. The engine had to be smaller, faster, and even more violent. It wasn't the signature of a death. It was the sound of a collision, a final violent waltz between two of the universe's most extreme and compact corpses. They were the brightest electromagnetic events known to occur in the universe, outshining entire galaxies for a fleeting, violent moment. But the mystery deepened when astronomers noticed these bursts were not all the same. Some lasted for minutes, a long, drawn-out cry from a dying star. But others were different. They were whispers. Impossibly brief, gone in less than 2 seconds, sometimes lasting only a few milliseconds. They were cosmic flashes so fast that if you blinked, you would miss the entire event. These were the short-duration gamma-ray bursts, and their cause was not a collapse, but a collision. Their story is not one of a star dying alone, but of a final violent embrace between two of the most extreme objects the universe can create. It is the story of a cosmic dance, a waltz that unfolds over eons, played to the silent music of gravity itself. Imagine in the dark expanse between stars, two ghosts. They are the corpses of giant suns that lived and died long ago, their cores collapsing under a gravity so intense that protons and electrons were crushed together to form a sea of neutrons. What remains are two spheres, each no larger than a city, yet each containing more mass than our own sun. They are neutron stars. A single spoonful of their substance would weigh more than all the mountains on Earth. They are objects on the very edge of existence, just shy of the density needed to become a black hole. And in this corner of the cosmos, two of them are locked together in an ancient orbit, bound by a gravitational grip of unimaginable strength. For millions, perhaps billions of years, they perform their slow waltz. They circle one another in a patient, silent rhythm, 2 points of impossible density in the void. From our distant perspective, nothing seems to change. The millennia drift by stars, are born and die elsewhere galaxies turn, and still the two neutron stars continue their serene, predictable dance. But it is a dance with a guaranteed, fatal conclusion. Because with every orbit, they are losing something precious. They are bleeding energy, not as light, not as heat, but in a far more fundamental way. They are radiating their orbital energy away as ripples in the very fabric of reality. Albert Einstein, in his theory of general relativity, imagined spacetime not as an empty stage, but as a dynamic, flexible medium, like a vast cosmic trampoline. Massive objects, he proposed, create dents in this fabric, and it is this curvature, we experience as gravity. But he also predicted that when massive objects accelerate, as these two neutron stars do in their constant circling, they should create waves, vibrations that propagate outward through the fabric of space-time at the speed of light. These are gravitational waves. For a century, they were a beautiful, unproven prediction. They were the silent song of the cosmos, a music we had no instrument to hear. As our two neutron stars waltz, they are constantly singing this silent song. They are churning the space-time around them, sending out a steady, faint hum of gravitational waves. This is the energy they are losing, and as their energy drains away, their orbit must shrink. Infinitesimally at first, the distance between them lessens by millimeters per year. The change is imperceptible over a human lifetime, but cosmic time is patient. Over millions of years, the slow, graceful waltz begins to quicken. The circles tighten. What was once a majestic, slow orbit taking hours or days becomes faster, tighter. The two city-sized stars, each heavier than the sun, now whip around their common center in minutes, then seconds. As they draw closer, the tempo of their gravitational song increases. The gentle hum becomes a rising tone, a cosmic siren's call that grows in pitch and intensity. In the final minute of their long existence, they are moving at a significant fraction of the speed of light. Space-time is no longer being gently stirred. It is being violently twisted and torn. The gravitational forces at play are beyond comprehension. The stars begin to distort each other, their spherical shapes pulled into teardrops by the immense tidal forces. The crusts of neutron-rich matter begin to crack and shatter, unleashing flares of energy. Then comes the final 3 seconds. They are now so close that they are almost touching a blur of motion. The gravitational waves they emit have become a roar, a final screaming crescendo that carries the news of their impending doom across the universe. In the last fraction of a second, the dance ends. The two stars collide. The impact is not an explosion in the way we typically imagine it. It is a fundamental remaking of matter and energy. The two seas of neutrons slam into one another momentarily, creating an object of even greater density, perhaps a hypermassive neutron star that survives for a few milliseconds before collapsing, or perhaps an immediate birth of a brand new black hole. In that moment of catastrophic collapse, a portion of the surrounding material is channeled by intense magnetic fields and blasted outwards in two opposing jets. These jets, traveling at over 99.9% the speed of light, are so energetic that they tear through anything in their path. If one of these jets happens to be pointed directly at Earth, we see it. We see that impossibly brief, impossibly bright flash of high-energy light. We see a short-duration gamma-ray burst. The lighthouse has flashed its beam across billions of light years, but the flash of gamma rays is only the beginning of the story. The rest of the material from the collision, a colossal cloud of hot, dense, neutron-rich debris, is flung outwards in all directions. This expanding fireball is not a supernova. It is something else, something rarer. It is a kilonova. This cloud of exotic matter, heavier than lead and hotter than the core of a star, begins a frantic and spectacular process of cosmic alchemy. In the first few seconds after the merger, within this chaotic furnace, the universe forges its most precious and heaviest treasures. Free neutrons are captured by atomic nuclei so rapidly and in such vast numbers that the periodic table is built up in the blink of an eye. This is where the universe creates its gold. All the gold ever mined on Earth, the gold in our jewelry, in our electronics, in our teeth, was almost certainly born in the heart of a kilonova, the aftermath of a neutron star waltz. The same is true for platinum, for silver, for iodine, and for uranium. These elements, so rare and vital to our planet and our technology, are not cooked up in the cores of ordinary stars. They require the unique violent conditions found only in this cataclysmic merger. The kilonova glows for days and weeks, not with the brilliant white light of a supernova, but with a dimmer fading red and infrared afterglow, the cooling embers of a cosmic forge that has just seeded the universe with new heavy elements. And across the cosmos, traveling for hundreds of millions of years, the final note of that gravitational song arrives. On September 14, 2015, for the first time in human history, our instruments were finally sensitive enough to hear it. The Laser Interferometer. Gravitational Wave Observatory, or LIGO, detected the faint stretching and squeezing of spacetime itself. We didn't see the collision, we felt it. We felt the echo of two black holes merging, and later on, August 17, 2017, we finally felt the signature chirp of two neutron stars spiraling to their doom. Moments later, telescopes across the world swiveled to the same patch of sky and saw the flash of the gamma ray burst, followed by the telltale fading glow of the kilonova. The theory was no longer just a theory. The cosmic dance was real. We had finally heard the music. So we look up at the night sky, at the silent, serene tapestry of stars, and we now understand the violent creativity hidden within it. We see events that are not just distant abstract explosions, but the very foundries that created the materials of our world. We hold a piece of gold in our hand and can trace its lineage back through time and space to a moment when two dead stars in a final frantic embrace seeded the cosmos with its weight and its worth. This metal was not born on Earth. It was delivered here, a gift from a cataclysm. And it is not just the rare and heavy things that connect us to these stellar events. The connection is far more intimate, far more fundamental. It is written not just in the ground beneath our feet, but in the very blood that flows through our veins. They were cosmic flashes so fast that if you blinked, you would miss them. Whispers from the edge of space-time, hinting at a violence so profound, so compact, that it defied the imagination. For decades we saw the long, mournful cries of dying massive stars. But these brief ethereal bursts of gamma radiation were something else entirely. They were the signature of a different kind of ending, and a different kind of beginning. And in the quiet aftermath of these thoughts, as the mind settles from contemplating such distant, cataclysmic events, a simple question may arise. What does any of this have to do with us? What does the death of a star, a billion light years away and a billion years ago, have to do with the gentle rise and fall of your chest as you breathe? What does a collision of stellar corpses in a flash of cosmic gold-making have to do with the feeling of stillness in a quiet room? The answer, it turns out, is everything. The story of these explosions is not a separate narrative from our own. It is our origin story. We are in the most literal and physical sense the living memory of these stellar fires. To understand this, we must turn our journey inward, away from the distant galaxies, and into the most intimate territory we know, the landscape of our own bodies. Let us begin with the air you just drew in, that breath, rich in oxygen, filling your lungs, giving life to every cell. Where did that oxygen come from? It did not exist at the dawn of time. In the beginning, the universe was a far simpler place, chemically speaking. The Big Bang cooked up the lightest, most fundamental elements: hydrogen, a little helium, and a trace of lithium. The cosmos was a vast, dark sea of these simple gases. It was a universe without rocks, without water, and without the possibility of life as we know it. For life's complexity, you need heavier things. You need carbon, nitrogen, and oxygen. You need a forge. And the first forges were the hearts of stars. For hundreds of millions of years, gravity patiently gathered the primordial hydrogen and helium into colossal spheres. In their cores, pressures and temperatures grew so immense that atoms which fiercely resist each other were forced to fuse. In the heart of a star like our own Sun, hydrogen atoms merge to become helium, releasing the light and heat that warms our world. As stars age, they learn new alchemy. Helium fuses into carbon. Carbon and helium fuse into oxygen. The oxygen in your lungs was born this way, inside the sweltering core of a star, at least 8 times more massive than our Sun. For millions of years, that star lived a brilliant, furious life, a nuclear furnace patiently building the elements of life. But for that oxygen to become part of a future world, to become part of you, it had to be set free. And the star's death was its liberation. As we have seen, when a massive star exhausts its fuel, its core collapses. The star dies in the most spectacular way imaginable, a supernova. In that final shattering moment of unbearable pressure and heat, the star blows itself apart. It casts its newly forged elements out into the interstellar void. The oxygen created in its heart over millennia is hurled across space in a blossoming cloud of incandescent gas. That cloud, the beautiful ghostly nebula of a long-dead star, is a seed bank for new worlds. It mixes with other clouds. It swirls for eons until gravity once again begins its patient work, pulling that enriched gas and dust together to form new stars, new planets, and eventually new life. The oxygen atom you just utilized was once locked inside a star, and it was freed by a supernova. Now consider your own body. Feel the sturdy, reliable framework of your bones, the hardness of your teeth. They are built from calcium. This too is a gift from the supernovae. The immense energies of the explosion are required to fuse lighter elements into the heavier ones, like the calcium that gives our skeletons their strength. A star does not need calcium to live, but we do. The star, in its final generous act, creates the very scaffolding of our bodies and scatters it into the cosmos. The skeleton of a star becomes the skeleton of a human, and then there is the iron. Think of the blood flowing through you, carrying that precious oxygen to every part of your being. The molecule responsible for this is hemoglobin, and at its very center sits a single atom of iron. It is iron that gives blood its deep red color. It is iron that latches onto oxygen in the lungs and releases it in the tissues. It is essential. And iron has a special place in the story of the stars. It is the final ash of normal stellar fusion. In the core of a massive star, the fusion process continues creating heavier and heavier elements, releasing energy at each step. But when the core turns to iron, the process stops. Fusing iron into something heavier does not release energy, it consumes it. And so the furnace goes out. Iron is the trigger for the star's collapse. The very element that chokes the life from a star's core is the same element that allows our blood to carry life through our own bodies. The iron atom at the center of your hemoglobin was in all likelihood forged in the heart of a massive star moments before it detonated. It was present at the scene of the crime, the very catalyst for the explosion that would eventually allow it to travel across the galaxy and find its way into you. So we are built from the remnants of these giant stars. We are breathing their legacy, supported by their bones, and animated by the very element that signaled their demise. But this is only part of the story. The alchemy of supernovae can only go so far up the periodic table. For the truly heavy and precious elements, we need an even more extreme event. We need to return to those mysterious fleeting whispers from the cosmos, the short gamma-ray bursts. We now know their cause, the collision of two neutron stars. Imagine it. Two objects more massive than our Sun, crushed down to the size of a city, spinning hundreds of times a second, locked in a gravitational death spiral. As they draw closer, they warp spacetime so violently that they radiate gravitational waves, ripples in the very fabric of reality. In their final moments, they collide with a force that is almost beyond comprehension. This is the kilonova. In the unfathomable heat and pressure of this merger, a process of cosmic alchemy occurs that is impossible anywhere else. It is called the rapid neutron capture process, or the R process. So many neutrons are flying around with such incredible energy that atomic nuclei are bombarded with them. They absorb neutron after neutron, growing heavier and more unstable before they have a chance to decay. In a fraction of a second, the universe's heaviest elements are cooked into existence. Consider a piece of gold, a wedding ring, a piece of jewelry, a fleck in a riverbed. Every single atom of that gold was forged in the crucible of a neutron star collision. It requires an event so violent it sends shivers through space-time itself. When you hold a piece of gold, you are holding the relic of a kilonova. You are touching something that was born in one of the most extreme environments the universe can create. The same is true for platinum, for uranium, for mercury. These are not the gifts of ordinary stars, but the rare treasures forged in the wreckage of stellar ghosts. And so the picture becomes complete. The story of the universe is written in your very form. Take a moment and reflect on this composition. The hydrogen in the water of your cells is primordial, forged in the first 3 minutes of the Big Bang. Itself, it is the oldest matter within you. The carbon that forms the backbone of your DNA and proteins was fused in the heart of a small star, a star that puffed away its outer layers in a gentle nebula at the end of its life. The oxygen you breathe, the calcium in your bones, the iron in your blood, all are the children of a supernova, the fiery death of a giant star. And if you wear a piece of gold, or even if you just appreciate its gleam, you are connected to the mind-bending collision of two neutron stars, an event that lit up a distant galaxy for a fleeting moment billions of years ago. You are not just living in the universe is living in you. Every element heavier than hydrogen was forged in a star, and we are made of those elements. We are walking, talking, thinking archives of cosmic history. Each of us is a mosaic assembled from the dust of countless different stellar events, separated by unimaginable gulfs of time and space. An atom of carbon from one stellar system rests beside an atom of iron from another, woven together by the gentle, persistent gravity of our own solar system, and then by the intricate chemistry of life. We are stardust. It is not merely a poetic phrase. It is a literal scientific truth. The universe, through the slow, violent, and beautiful cycle of stellar life and death, developed the capacity to become aware of itself. It grew the carbon for thought, the iron for blood, the calcium for structure. And then, on a small, quiet world, it assembled them into beings who could look back up at the night sky and wonder where they came from. This connection is profound, a source of deep belonging. But it also reveals a universe that is both creative and destructive in the very same breath. The explosions that created the building blocks of our bodies are forces of unimaginable power, sterilizing entire regions of space. The supernova that seeded our region with iron could have just as easily scoured the life from a nascent planet. The gamma ray burst from a neutron star merger is one of the most lethal phenomena we have ever discovered. This brings us to a new, more delicate question. We are made of the fire, but how did we manage to survive it? How does life find a safe harbor in a galaxy filled with such creative violence? Our existence seems to depend on a fragile balance, close enough to the stellar forges to receive their gifts, but far enough away to avoid their lethal power. To understand our own story, we must now look not just at the events themselves, but at our place among them within the quiet, gentle shallows of our own galactic home. And in the quiet aftermath of these thoughts, as the mind settles from its voyage to the edge of space-time, we feel our awareness begin to drift back from the violent birth cries of black holes and the fury of colliding neutron stars. We return not to where we started, but to a place of deeper understanding, carrying with us the echoes of these cosmic tempests. The mind, having witnessed such power, now seeks a place of perspective, a place of safety from which to contemplate it all. It asks a simple human question: are we safe? The answer, written in the very architecture of our galaxy, is a quiet and profound yes. To understand this safety, we must learn to see our galaxy not as a static jeweled disk, but as a living, breathing ecosystem. It has its own geography, its own climates, its own intricate weather patterns of creation and destruction. The bright, swirling spiral arms are not merely decorative. They are the galaxy's storm fronts, regions of immense turbulence and activity, where vast clouds of gas and dust are churned, compressed, and ignited into blazing new stars. This is where the stellar giants live their short, brilliant lives and die in spectacular supernovae. These are the active, bustling, and often violent industrial zones of the Milky Way. But we do not live there. Our home, our solar system, drifts through a calmer, more temperate region. We are situated in a quiet, unassuming provincial arm, far from the chaotic weather of the main spiral lanes. Think of it as a sheltered bay, a peaceful harbor on the coast of a vast and stormy cosmic ocean. From our protected vantage point, we can see the flashes of lightning from the distant storms, the supernovae, and the gamma ray bursts. But we are shielded from their immediate fury by the sheer, unbreachable gulf of space. This fortunate placement is part of what astronomers call the galactic habitable zone. It is a concept born of balance. If we were too close to the galactic center, the environment would be simply overwhelming. The density of stars would be immense, increasing the chances of a catastrophic encounter. The background radiation from the supermassive black hole at the galaxy's heart and from the constant barrage of nearby supernovae would be far too intense for life as we know it to take hold. It would be like trying to build a delicate sandcastle in the middle of a permanent hurricane. Conversely, if we were too far out on the desolate fringes of the galaxy, life would face a different challenge: starvation. The outer regions are poor in the very elements forged in the hearts of stars and scattered by their explosive deaths. Carbon, oxygen, iron, the building blocks of planets and of ourselves, would be too scarce. It would be a cosmic desert, beautiful and empty, but lacking the raw materials for complexity to arise. And so we find ourselves here, in this gentle, temperate band, not too close to the fire, not too far out in the cold. A region where the storm of star formation has passed through just enough times to enrich the local environment with heavy elements, but has now settled into a long, predictable calm. Our sun is not a dramatic, short-lived giant, but a stable, patient, middle-aged star capable of nurturing its planetary family over billions of years. This stability is our greatest inheritance. The vastness of space becomes not an isolating void, but a protective cushion. A supernova would need to occur within about 50 light-years of us to pose a significant threat to our atmosphere, to strip away the delicate ozone shield that protects us. And in our quiet cosmic neighborhood, stars massive enough to produce such an explosion are exceedingly rare. The storms are almost without exception happening somewhere else, far across the ocean. Even the terrifying power of a gamma-ray burst is tamed by distance and probability. These events, as focused and deadly as they are, must be aimed almost perfectly at us to cause harm. They are like cosmic needles in a galactic haystack, and the chances of our world finding itself in the path of one are infinitesimally small. The universe in its grand violence is also governed by the saving grace of immense scale. Time and space are our guardians. The light we see from a distant supernova tonight is the ghost of an event that happened hundreds of thousands or even millions of years ago. We are watching ancient history unfold from a place of profound safety, but this safety is not a sterile isolation. We are deeply connected to the very events we are shielded from. The creative power of these cosmic explosions is in fact the reason we are here at all. A supernova does not only destroy, it gives birth. When its shockwave rips through the interstellar medium, it does not just scatter the old. It acts as a cosmic plow, sweeping up diffuse clouds of hydrogen gas and cosmic dust, compressing them with unimaginable force. Imagine a vast invisible cloud adrift and stable for eons. The shockwave from a nearby stellar explosion crashes into it. This sudden violent squeeze is the trigger. It pushes the gas and dust together, increasing its density until gravity's gentle, persistent pull can take over. The cloud begins to collapse in on itself, fragmenting into smaller, hotter, denser cores. These are the seeds of new stars, the protostellar nurseries. One of those seeds billions of years ago was our own sun. It is a beautiful and humbling thought. The birth of our solar system was likely triggered by the death of an unknown, long-forgotten star. The shockwave from its final convulsive act provided the necessary push to begin our own story, and the explosion itself seeded the collapsing cloud with the precious heavy elements it had forged in its core. The calcium in our bones, the iron in our blood, the oxygen we breathe, all of it was created in a stellar furnace and delivered to our nascent solar system by the very same kind of cosmic cataclysm we have been exploring. We are not just observers of the galactic weather. We are born of it. The storms of the past are the reason our quiet harbor is so fertile. The echoes of ancient explosions are written into our very DNA. This transforms our perspective. The distant flash of a supernova is no longer just a spectacle of destruction. It is a reminder of the universe's cyclical nature. It is the death that makes new life possible. It is the closing of one chapter and the violent, beautiful, necessary beginning of another. It is the galaxy regenerating itself, turning the ashes of the old into the foundations of the new. Our place in the cosmos, then, is one of extraordinary privilege. We exist in this delicate balance, this galactic habitable zone, protected by distance, yet enriched by the creative fallout of cosmic history. We are safe enough to evolve, to wonder, to look up at the night sky and piece together the story of our own origins. We can witness the distant cosmic fireworks, not with fear, but with a sense of connection and profound gratitude. The universe is not a quiet or gentle place, but it has its havens. It has its quiet shores where the waves of creation and destruction break gently, leaving behind the raw materials for thought, for consciousness, for life. And so, from this peaceful harbor, having looked out at the farthest and most violent shores of the cosmic ocean, our awareness begins its slow, gentle journey home. We have seen the great cycles of stellar birth and death, and we have found our own small, safe place within them. The mind filled with the scale of galaxies and the echo of starlight now turns inward and downward, returning from the cosmic horizon to the personal one that awaits us right here. It arrives. The mind, having witnessed such power, now seeks a place of perspective, a place of safety from which to contemplate it all. It finds a quiet shore, a familiar horizon where the great dark ocean of space meets the steady ground of our awareness. We stand here at the edge of that ocean once more. Do you remember this place? We began our journey here, looking out at the calm, dark surface, sensing the quiet potential that lay beneath. It was a stillness of mystery, a peace born of the unknown. But now, as we return, the stillness feels different. It is no longer the peace of ignorance, but the peace of understanding. The water before us is just as dark, the surface just as placid, but we know now what storms rage in its depths. We know that the gentle lapping at the shore is the faintest echo of tidal forces warped by neutron stars, the quietest whisper of shock waves from a supernova that bloomed 1 billion years ago. The darkness is not empty. It is a plenum, a vast reservoir of creative violence held in a delicate and temporary truce. Every gentle swell on this cosmic sea is the endpoint of a cataclysm. We look upon the same tranquil scene, but we see it with new eyes. We see the gamma ray burst that for a few brilliant seconds outshone its entire galaxy, now reduced to a subtle ripple in the fabric of space-time, passing through us without a sound. We see the titanic collision of 2 white dwarfs, a type Ia supernova that served as a standard candle to measure the universe itself, now just a soft fading glow in the unfathomable distance. The calm has not changed, but our perception of it has been forever deepened. It is the calm of a sleeping giant, the quiet of a foundry after the crucible has been poured. This peace is not the absence of chaos. It is the thoughtful contemplation of it from a safe and distant shore. Lift your gaze from the water's surface to the sky it reflects. The canopy of night is no longer a simple collection of glittering points. It is a museum of endings and a nursery of beginnings. Each star is a story, and the space between them is the memory of stories that have already concluded. That faint star nestled in the arm of the Milky Way might be a sun like our own, steadily fusing hydrogen into helium, blissfully unaware of its own eventual quiet demise. But the one next to it, tinged with a reddish hue, is a giant living on borrowed time. It is a bomb with a very long fuse, and when it finally detonates, it will seed its entire cosmic neighborhood with the elements of life. The light that reaches your eyes tonight is ancient. It is a ghost, a messenger from the past. The light from the nearest star, Proxima Centauri, began its journey to you more than 4 years ago. The light from the Andromeda Galaxy. Our closest major galactic neighbor has been traveling for 2.5 million years. When that light began its voyage, our own species had not yet fully emerged on this planet. We are, in effect, looking into a time machine. The sky is not as it is, but as it was. The explosions we have witnessed on this journey, the supernovae, the kilonovae, are still happening out there right now. But their light, the news of their occurrence, will not reach this shore for millennia, for eons. And so the night sky becomes a profound lesson in patience and perspective. It teaches us that events of unimaginable significance can unfold without our immediate knowledge. It invites us to hold a larger frame for our own lives, our own urgencies. What feels all-consuming in this moment is in the grand narrative of the cosmos, less than a single breath. This is not to diminish our experience, but to unburden it, to see our own struggles and triumphs as part of a much grander, much older story, can be a source of incredible freedom. We are not the center of the story, but we are a meaningful part of it, a rare and beautiful moment of awareness in a universe that is mostly dark and silent. This connection is not merely poetic. It is physical. It is literal. Think of the elements that constitute your own body. The calcium in your bones, the iron in your blood, the oxygen you are breathing in this very moment, none of it was created in the Big Bang. The early universe was composed almost entirely of hydrogen and helium, the simplest of elements. Everything else, every building block of the complex world we know, had to be forged. And it was forged in the heart of the stellar furnaces we have just explored. Every heavy element was created in the crushing pressure of a star's core, or in the explosive fury of its death. A supernova is not just an ending. It is a grand act of cosmic recycling. It is a star sacrificing itself to enrich the universe. The iron that allows your blood to carry oxygen was born in the final violent moments of a star many times the mass of our sun, which lived and died long before our solar system ever formed. That star's death throes cast these precious elements out into the void, seeding a nebula of gas and dust. And from that enriched cloud, new stars and new planets, our sun, our earth, were born. You are in the most direct sense imaginable made of stardust. The atoms that make up your hand were once scattered across interstellar space, the remnants of a cosmic explosion. The universe is not something external to you, something to be observed from a distance. You are the universe experiencing itself. You are one of its methods for turning nebulas and supernovas into curiosity, into wonder, into love. The violent creative heart of a star beats within every cell of your body. Let this thought settle not as a grand abstract idea, but as a simple physical truth. Feel the warmth in your body, the steady rhythm of your heart. That is the legacy of the stars. That is the quiet fire they passed on to you. With this understanding, let your awareness gently return. Return from the edge of the galaxy, from the event horizon of a black hole, from the brilliant flash of a dying star. Let it travel back through the silent gulf of space, past the orbits of the outer planets, past the moon, and through the soft blue veil of our atmosphere. Feel your awareness settle back into the room you are in, into the physical space you occupy. Become aware once more of the simple grounding sensations of the present, the feeling of the surface beneath you, holding you, supporting you completely, the temperature of the air on your skin, the gentle, effortless rhythm of your own breath rising and falling like the quietest of tides. Each breath is an anchor to this moment, to this body, to this life that is woven from the fabric of the cosmos itself. The journey outward into the vastness of space was always in the end a journey inward. It was a way to discover the universe that resides within you. The storms are still raging out there in the deep. Stars are being born and stars are dying. Galaxies are colliding. The great cosmic engine of creation and destruction continues its work utterly indifferent to our existence. And yet, here we are, a fragile, temporary arrangement of stellar debris, capable of looking back at our own violent origins with a sense of awe and gratitude. This is the miracle, not the explosion, but the reflection upon it. The night is still, the ocean is calm, and within this profound peace, you can now feel the echo of 1,000 billion stars. You can rest knowing you are a part of this grand cyclical story, a story of fire and dust, of endings that are always beginnings. And in the quiet moments before sleep, if you listen closely, you can almost hear the silent, patient music of the spheres, a symphony of creation that has been playing since the dawn of time, and which for a brief and precious moment is you. Thus, as our journey through the stellar forge comes to a close, we are left with a quiet sense of perspective. We have stared into the most powerful and creative crucibles of the cosmos and found not a reason for fear, but a reason for connection. The universe, in its incomprehensible scale and power, is not a distant sterile machine. It is our home, our source, our ancestry. The same laws that govern the collapse of a star govern the beating of our hearts. The same elements forged in cosmic fire give warmth to our bodies. In understanding the sky, we understand a deeper part of ourselves. May this perspective bring a sense of peace, a feeling of belonging to something immeasurably vast and beautiful, and may the light of the most distant stars illuminate your own inner world with wonder and tranquility.